Hello, gentle readers. Welcome to another episode of Logos 2000, with the subject of discourse being 21st century foundations, logical, philosophical, mathematical, scientific, physical, natural, for reason and rationality, wisdom and intelligence, and knowledge, and theory. Theoria is a word, and it represents a state of the concept of theory and thinking of a theory. Besides thoughts and beyond thoughts is matters of contemplation and deliberation. The idea of theory itself is sort of a grand thought that encompasses reasons, often after first principles and final causes. The reasons for things, that in this logical and technical theory that reasons and rationality are the same thing. It's like they say about mathematics, there are right and wrong answers. So in this sort of theoria, which is often as well affected to intend contemplation and deliberation in the universe of things, here's for the technical analytic, as for an ontological universe of things, for as well a teleological and an absolute world of things, then as with regards to what is appreciable, comprehensible by philosophical man, thinking beings here in the course of these things. So there's not much to it today in Logos 2000. It's just I have some books here, and so I'll just be kind of looking at them as kind of a lull, say, from some of the more meaty, weighty accounts as of the recent issues of Logos 2000 that include, for example, things like Hegel's Wissenschaft der Logik and about axioms natural deduction and a theory overall that can be consistent, complete, and concrete. With all the diversity and variety is after the axiom of inverse, say, which arrives at a brief account for the usual fundamental question of metaphysics to arrive at one and carry on from that directly to axiomless geometry, which then sees directly fulfilled immediately Euclidean geometry, which is usually considered the mathematics and a key point in the theory. So thusly, today then there'll just be kind of some reading of some books, as from all gathered various sources, what may so intend to inspire some kinds of thoughts. Well, the first little book here is a programming manual. And so one of the acts of doing logic, carrying out reason and rationality, is to embody it in the form of a program structure with regards to then that given models of computation or models of process and computation or computators, as they might have said in the 1950s, when computators was kind of a new word. It meant like mechanical, electronic computers, vis-a-vis the old word computer, meaning just to compute, what computes, to make sums, but otherwise to carry out mechanical inference, rules defined by a mechanism of inference. That this is a little programming manual. This is for one of these languages called Practical Extraction Report Language, a backronym for Perl, Larry Wall's language of scripting. It's an interpreted language vis-a-vis a compiled language. Has that a compiled language is arbitrarily rendered from a source text to an object file in a sequence of zeros and ones called binary. To the binary is what is compiled. This program form with its entry point and any number of exit points, and libraries and symbols as ordinals, is with regards to the entry points usually in object files that are loaded and linked to programs according to the most usual sorts of computer architectures. That a compiled program would be when you think about languages like assembler or C or C++, their output is to one of these machine files. Whereas a Perl program is similar to Ruby or JavaScript or Python or other interpreted languages have that every time that the program is run, every single line, kind of like as in a shell script, is kind of interpreted a piece as with regards to what's compiled and built. And of course that can incrementally compile and build data structures, and then those invoked is by the program model and the process model of routine and multi-programming and multiprocessing environment, usually of a single computer or node, this kind of program. As regards to then that Perl is a great little language. And what it has is it has the usual abstract data types of the associative array, which makes for an array. So after the built-in types, what are often called scalars, after Java kind of said that, well, there are scalar types and there are vector types, and then as of those, there are usual default built-in containers. That in many of these languages, the usual idea of an object is just an associative array, which means it has key value pairs. That A is for apple, B is for boy, C is for carrot, and these kinds of things. An associative array, vis-a-vis an indexed array by numbers, like 0 is apple, 1 is boy, 2 is carrot. That an array and an associative array are so ubiquitous and used in all the languages that they're almost always either built-in types or even like default and de facto types. In a language like Java, which is kind of halfway between interpreted and compiled because it has an intermediate format called a bytecode representation, that it's rendered into a form that's not quite machine code, that runs actually according to the register transfer logic and the instruction pointer on the chip, and the interpreted, which runs within the interpreter and as it is parsed and it's lexical and as up to the syntactical, making up the program line by line. The Java is kind of in the middle, then has a language like Java is also object-oriented, and it has one root-based class of all objects. So it uses type theory to define classes, and then classes are defined by their types. And this makes a very strong model of the representation of objects because they're always of a particular given type. So in other languages like JavaScript and maybe Ruby and Python, it could be said that these kinds of hashes or tuples or objects, they call them, are just associative arrays. So the associative array, or the map class, it's sometimes also called the map, is basically entirely just made abstract as like it's a list of key value pairs, and in some representations it might be only a set of keys then that have values apiece, and that's usually the idea, is that each key is unique and then only has one value. It's an associative array in this sense. Each of these maps or hashes or objects in JavaScript and these kinds of things, that all these languages have then this same data structure as their root kind of thing. And it's not dissimilar in languages like Java that have member fields of classes or structs, that in these structs, which make for structured programming, is how it's arrived at, that there are these member fields, and so then these fields are like a key, and then they have a value according to the name of the field and then the value of this field. So the associative array is basically the most fundamental object in these object languages. So Perl has a great way to appreciate that for a given label of a variable, then it has three different accessor methods. One for being the scalar, like this is the name of the object. The other being for like it's a list or a tuple, and another being as for reference. So Perl has got some funny syntax, and it uses punctuation as these being reserved letters of a sort, and thus by indicating the access and the reference and dereference of the variables, that it automatically builds the hashes, as they're called in Perl, or also these ones about just scalars and these other types have their own sort of access. And then similar, some of the built-in types like file system objects, and these also have their own particular syntax and semantics in the language. And so that just helps to effectively reflect that different languages are designed with kind of different perspectives and different expectations, and then different syntaxes with regards to their semantics. And then they all build down kind of the same program model because it's eventually a machine model. And so then when there are certain facilities like the file system or a database or a message queue or web services, then these adapters kind of reflect in these boundaries and the layers of these kinds of things in terms of program design. And then for the uniprocessor, which is like a single unit of computation, and then the multiprocessor environments, and then the distributed environments, which reflect independent units of computation that communicate these messages via messages, and as with regards to communicating sequential processes. The theory of distributed computing is basically often described as communicating sequential or serial processes. Thus, everything operates in parallel all the time, each according to their own clock driver, or what actually is the systolic, like the heart is a systolic pump, that the systolic clock drives the motion and carriage of the instruction pointer on each of these processing units. That each program has this entry point and any number of exit points, and oftentimes those to be returning the value of these routines or procedures or sub-procedures or subroutines. The pieces that together add up to making an algorithm, say. And then that languages like Perl are pretty carefully defined and help to describe different aspects like dealing with records, with their fields, and something like all the ways to deal with like a table-oriented data of things, vis-a-vis record-oriented things, usually often with regards to rows. So it's lines, and each one line is a row, and then those make rows. And then they have columns, and often like a column headers, say, and then they each have what results as tabulated data, or the tabular data. And thusly in the data then is often for line feed data is often just like, as you might imagine that a printer prints a line at a time, then the output of this thing is a given list of these items. For example, the values of another given object's row, where the column headers are the names of these attributes in an associative array, helping to reflect that there's the great transpose between an associative array, which is an instance of an object with keys and values, and the columns and rows, where the column headers are each of the keys, and then a value is just the values for each one of those keys of a row, say. So languages like Perl, for practical extraction and report language, which is not really its name, it was originally after like the Perl of Great Price or something, whatever, Larry Wall, the author who wrote this whole language and wrote the interpreter as a program itself, it's just another program, and then built this interpreter so it runs on many, many different kinds of computers, that the same interpreted program can run on many, many different kinds of computers because it has an interpreter that's compiled specifically to each one of these and plays the facilities of the resources of this resource model of the model of computation, the process, and a program model of the things, of the space and time, the space being how much disk or memory space, and the time being how much of the central processing unit and general purpose instruction carriage can carry it out. And then for also I/O, and then the network connecting as via a naming interface, a naming, and this also a routing to each of these other computers, and then connecting them by these processes, usually via a model called sockets, just kind of like wires plug into sockets in the wall and then connect to others, then it's so similar with this in terms of clusters of computers all connected together. Then this language is a handbook of the language, and then it's libraries. And so what it does is it's really just kind of a brief reference manual, and it helps to establish for you all these different many tables, listings of the contents of the syntax and their purpose and their use, so that then thusly all these different things that go into learning a language go to adapt it. First, there's these concepts of like the program model and the process model and the resource model and a model of computation. And for a program model, then it has its inputs and outputs as regards to the facilities and the resources like files, databases, message queues, and web services, that thusly it can result to arrive at what's made for these then is how each of these different languages adapt to these same resources. And so when I first started to learn this language, it was in a computing environment where there are already many hundreds and thousands of programs written in this. For example, for like an online retail web store system, say. And so in that sense, it helps a lot that there were a lot of great examples of how a structured program emerges from these approaches, and how one would say these practices to arrive at what would be a rich body of code, the corpus, up into beyond the lines of code, the thousands of lines of code, the millions of lines of code, the months and years and decades of man years that went into writing this code, has then it's all embodied as this great file of files of all this code. So for example, here's it's just talking about like the usual string model of an object. Well, what's that, you might ask? Well, what it is a string of letters connected together. So a string in pretty much every language means one thing. It means a sequence of letters in a sequence, in a row, from beginning to end, a finite sequence of letters. So the other objects besides the associative array, which is the very common object of all these different languages, is that they have the machine types usually of the integers and numbers, integers and floating point numbers almost always. And then the string type is very much just meaning that it means a word or a paragraph or any list of letters and numbers and punctuation, anything in the character set that according to then a character encoding and various ways to encode the data, as kind of mentioned when discussing Unicode in the previous talk about Unicode 4.0, has that a string is just words. And so a computer program only has these three basic types to wonder about at this time. An associative array, which is like, and it's also called an object sometimes, or a map, but it just means a list of keys, meaning the names of the fields, and then the values of those fields. And so then there's numbers, and then there's strings. So in almost all languages, those are fungible data types, and they're built-ins most usually, meaning they don't take too much more to use them or declare them. Like in a shell scripting, you might indicate an array by its an assignment or declaring that of certain variables of a given type, that otherwise it's just a string. By default, everybody thinks in that. And it's almost always written in source code as in double quotes. So between double quotes, whenever you see a word or a sentence or a paragraph in double quotes in source code, it means a string literal. And so the literal is different than the identifiers of the source text, because the source text is the names of things. Somebody once said that the art and science and practice of computer programming is just giving everything its name, and then declaring how it operates in terms of definition, and after declaration, in the program model, the resource model, its names, and it's the art of naming things. So that's kind of on the lexical side, as for after the scanning and parsing and reading characters of the source text, because it's just kind of a string, it's just character data. And then when you see a literal, like the number 1 written by itself, or sometimes the word true or false are also Boolean data types, so they might be considered as 0 and non-zero sometimes, say. But they may be built-ins in first class in that sense. And then there's string data, is character data everywhere. And so whenever you see words in source text and it's in a pair of double quotes or single quotes in some languages, or triple quotes, or variously according to the language and how these are written in the source text, that then this is like the most usual milieu of all the source languages. Like all the source languages mentioned so far have it this way. This is part of the lexical content and the syntactical content of these strings. So what this starts with is a section about quotes and interpolation. And so before getting into quotes, is that quotes have what's called a syntax for escape. And so what this means is that in a string, if you've written it in double quotes, it begins with a double quote and it ends with a double quote. But what if it actually contains a double quote? Well, then if you were reading beginning to end, then that would stop right there, and there'd be no way to tell unambiguously whether it was the actual end of that string or if it's actually contained in the middle of the string, that actually the string contains what are its delimiters or what are its syntactical escapes, or that would establish this syntactical scope of expecting to scan and parse lexically one of these items, a string. So what they have is one particular character usually is called an escape character. And this one is almost always backslash. So forward slash and backslash, or the solidus and reverse solidus, are almost always have in most of these languages that when to type a reserved character, or in a character that needs to be escaped in this escapement, kind of like a watchworks or something like that, within the literal writing of the string, is before there's that double quote in the middle of the string, there is the backslash. So the backslash is kind of like a silent character. But when you're reading forward, you just discard that and then interpret the characters immediately following it. For example, the letter B to make a bell, or a new line or carriage return, when there are lines actually embedded in the same string. This is a part of the encoding, that it establishes a different mode of the encoding and decoding of this literal string in the source text. Thusly, it's possible then for a scanner or parser, a reader of this, to notice that, oh, this escape character exists within the string. So what follows it is interpreted according to that, and then it goes back to its normal mode up till the end of the string, as indicated by an unescaped quote. So that kind of explains what has going on with quotes. And then this book, for example, lists some of the quoted characters and their escape sequences: the ASCII bell, the backspace, the escape, the form feed, the new line, the return, and the tab character. So these are almost all from the old typewriters, mechanical typewriters, and these are built in terms of ways that the platen rolled around and set and made for carriage return and line feed, and like the old manual swing to like start a new line, and the mechanical settings of the tab spaces. So every time you press T for table, tab for table, it would move to the next tab stop in the lines. That then as that went to computer feeds, then we have what's called form feed. So there's new lines and carriage returns, which both mean the same thing. It means to take the carriage and return the carriage, now that I'm reminded of it, and to both move to a new line and to return the carriage. The platen is what sat atop the piece of paper as it was rolling over the carriage to keep it from flopping. And so then there was just like a little window where you could see what you were typing as each letter struck it, that it was kind of the way of the things. And the computer printers, it's the same kind of thing. And for computer inputs, it's the same kind of thing. Because as records are read off of an input feed, then they're just considered as with regards to these things. So these are the most usual characters. And then there's also a way to make an escape for like a 4-digit Unicode number. And then so it's like \U and then these 4 hexadecimal digits. And that's to entail like one number. If like the 2020 in hexadecimal was the 480 character from mathematical symbolry or something like that. So that just helps to affect that there's a source text. It's got syntax of a program from beginning to end. It usually starts with an entry point, but it can have different routines or modules within it. They have their own. And then the idea is that then it just is sequential there, and then it's read off these ones. And these languages are much this way. So then, for example, like something like this, these string escape sequences are the same in every language. There are lots of things in the languages that are all the same in all the different languages. But then learning like which one is single quotes and which one is double quotes gets into one of these next ideas here of interpolation, which means that sometimes when you'll have different other characters or syntactical constructs that'll indicate substitution placeholders. So besides escapes, which just reflect literals to meaning that is to be understood as being another literal when it's actually the body of this character data, then interpolation or substitution is to encounter something like a $sign and then curly braces, and within that a name of a variable. And then wherever you see that, just replace that with a variable that's in the scope. So the scope means like, here's a list of all the currently visible words and their values, the variables and their values. And then as with regards to interpolation, this is one of the things that was very powerful in Perl, because that was when it was kind of new to have something like that. Although it's copyrighted off shell scripting and stuff like that. That this kind of book helps to explain all these different features, which are in every language, how they're done in this language. And so it's useful when you're having to deal with many languages, like in a typical workday, when you work in computer programming, you might see 10 different kind of source languages. And then have each one have their own things that are common. So you could write a parser that's for the common parts all the same, and the shared behavior of all these things. And then for the particularities or the specificities of each one, their own thing. So this is a pretty cool little book. And then it gets into, as these kinds of things would, with regards to how to access variables and reference and dereference variables. So from the C and C++ based languages, then it's key to learn how pointers work. And pointers is one of those difficult concepts to begin to learn, because otherwise when you're reading a text, it's not like a choose your own adventure, follow your own adventure kind of work where it's like, pick a path, go to A or B, which page to start reading again, because it's always just beginning to end. Beginning to end is how things are read, serially, sequentially. And so pointers and references and dereferencing the pointers make for like that in this variable is actually the name or the address of another variable. So given a variable, you can take its reference, and then so you can find where it's like the number that in the whole space of the memory is where that value sits. So it's no longer just the value in the scope, it's a value in a space in memory. And then when you dereference that, then it points to that value. So then you get back that value, or it can set or receive that value to get or set the accessor, and that is of whether the mutator to get or set the value of these things. So then this language has a pretty rich complement of ways to affect references to variables. And so that's what it gets into in part of the syntax. Then it has other deals to do with like files and file handles, because when you think about a language like that addresses kind of like the Unix model of a program model and resource model, so everything's a file, And what that means is that it's got a name and a namespace of files, and so that's like the persistence and the storage, and it's the existence of objects. They're called file system objects, or FSOs. So all the different languages have different ways to do that. It's usually called standard input output, or STDIO. So that's just gets into how to deal with these things with regards to these file handles. And so this language was built in with all its flow of control, and then how to define routines and subroutines, or functions, or in static routine, static methods. With regards to packages and modules, which are ways to make names and namespaces, are these things like this is a car, and this is a truck, and so they have different namespaces for things. But then within them, they might have the same ones. Or you might have it like this is a garage, and within it you might have a car or a truck. To consider the abstraction of these things, to name them pretty much what they are to represent, that then to be able to refer to like the driver's side window of the car and the driver's side window of the truck is two different things according to a namespace, where it's just driver's side window and driver's side window within that namespace. A namespace is just a hierarchical way to say from some root in these leaves of this directed acyclic graph, there are these things. So this is kind of just discussing usual ideas that are concepts in understanding. It's called code understanding source text, and then also what they mean, and how they result being defined behavior, what they do on resources. So that's a large and short of it. But this book just goes to address how these things are set up and all the cool different ways that they have of this defining all these things with regards to objects and special classes, functions, and then it gets into the whole standard library of functions. These are often available routines and meant to be usable for all kinds of math functions, for to get the time of day, to read variables, values off the strings, like to iterate, to get an iterator, or to iterate through each of the values serially of a string, or to get by an offset that a given sequence or array but will have an offset, and then that can be used to indicate like for the index and offset, those often being the same words for offset, and then that for a given base, which is like a place where its space begins, kind of like a namespace, but just like an offset, which is 0, it's a coordinate space, say, and then the offset from that indicating where a particular letter in a word is in all the giant space of memory. Because usually these days the whole computer's whole memory is just one wide space of billions and billions of zeros or ones, but billions and billions of bytes in it, and each one of those is used to represent a character or so, and so that a given string, like somebody's name, will just be at some offset in memory and be those next so many letters of their name. And so this just goes to show that then when referring to it, you think of it as just as value as a variable, but it's just and it's got a literal value. It's the content of the letters of that string. And then it actually sits and lives somewhere in memory, and the program has built into it its behavior to keep that back and forth, and to find space for it, and where it goes, and how to put them in order, and all these different things. So that's usually considered part of the libraries that do these kinds of things, like to make a list of names, or a set of names, or an associative array, or a map of these names. How it all goes to show that these libraries and standard libraries and all these languages, which almost all have all the same functions by just slightly different names and their parameters, which and the order of the conventions that they're passed and returned, how these things are, that the many things are very, very standard and the same for most of these languages. Then it has templates, like as part of substitution placeholders and formatting. That formatting is a great way to say, I want to print a rendition, a rendering of the data, and it must be formatted like so. Like these are dollars, and so it ends with 2 decimal points. And I want to see a 0 in the front of it if it's 0. And I only want to see a negative sign in front of it. Or maybe instead of a negative sign, I want to see it in parentheses if it's negative. Vis-a-vis, otherwise these things called formatting, which then have placeholders that then are a little language in their own little scope as their own little syntax, are read like the escape characters to read these formatting characters to go along with the substitution placeholders that are then interpolated the values when the function results like from an input and from a template an output. So then that's also often called the input process output model of an algorithm, say. Uppercase and lowercase, when you say, I'd like this string, but I'd like it to be in uppercase or lowercase. Many examples of functions on the arrays, function on the associative arrays and the hashes and objects. Regular expressions is matching. So on the other side of formatting, to make something as the output you want it to be is matching. When you want to establish is like, does this begin with A or B or C, or does it have the string ABC as a substring within it? The regular expressions is another feature that is after the what's called formal methods and formal automata. There's acceptors and rejectors. And so regular expressions are actually a particular kind of syntax. In the language of the syntax in formal methods and formal automata and acceptors and rejectors, there's different kinds of languages, and one of them is kind of like a right linear language, or the effect that you can read them only having to go forward. Like you don't have to read and then go back and then backtrack and try and figure out what's in the middle, which is how you naturally read things in words. But that a tiny machine that can only iterate forward can then, given this rule for matching by a regular expression, also called regex or regex, R-E-G-E-X, regular expressions, that then it can find if it matches or as accepts or matches or rejects. Either way, in so few resources, any of these different kinds of things. And so thus they can define functions and predicates, say matches or not matches. And then when you have an algorithm, you say, well, I want everything that starts with A to be like so. And if it matches, then carry it out. That regular expressions are as well part of the most usual sorts of things. Whereas as well, you could just iterate over a sequence and say, and test its value and say, is it A? Then that's the case. If not, then it's part of flow of control. So the acceptors and rejectors that are built in this way are just a way to make predicates that devise flow of control, which is it starts and it goes forward in the flow. And then this flow graph shows, well, if there's this, then do that, else do this other. And there's do something again and again in a loop. In these loops, there's do while something is true, and then there's while something is true to do. They just kind of checks the condition before or after each body invocation of the loop. There's totally standard keywords that break out of the loop or continue to the next iteration of the loop. So the flow of control, of course, is a great thing. And then many languages have exception handling. This is like deep within the trail of the program. It's like something broke, then it escapes or exits the way out until something catches the exception. So that's one other thing in the whole bracketing of the whole scope of the flow of control and the instruction pointer all the way on the machine, that when it reaches this condition, then it's able to escape not just out of a loop, but all the way out of a routine and out of a module. Not all languages have exceptions. It's a special kind of feature. But otherwise, it just goes forward, and then eventually it either exits or it enters a loop and carries out its routine, or it exits. And that's kind of how these things go. So regular expressions, search and replace is like interpolation, file operations, printing and formats, variables, tying variables, which is a cool thing in Perl, you can make something a variable. It looks like a variable, but actually it calls a function to get and set the value of the variable. So it just hides the value that otherwise you just say equals, like this equals that. And by saying that, you've assigned it to it. And this actually would just call a function, which would have the same purpose. Direct files and directories. So in the namespace of files, they're called directories, and they're a different kind of object, but they are just another file system object. System functions calls like exit, which means just exit, and that's always defined in the process model thing about the process IDs and group IDs and signals and the priority, which is like how much resources it gets to run and these kinds of things. Networking, because then that's all the stuff to do, connect to other computers and to communicate with them. Databases, then a database is a particular way to store tabular data in a big namespace of those and to access them. And how to run the debugger, meaning show what it's doing as it does it, so you can kind of get an idea when something goes wrong, what it's doing to arrive at that. The debugger, so it's got the compiler and debugger figured out, and then all these different libraries that then offer functionality and expand the functionality. So anyways, this is just a great example of a little handbook, a pocket reference for a language, because given all the concepts of programming, then all you need is something like a reference to its constructs, its idioms. It's called the idiomatic of the language, of its syntax and semantics after its lexical content, and for its program model as after the model of its source files, which is usually always just in files and directories, and then the packages and modules making for routines and modules. It's all modules to then arrive at flows, the flow graph of any of these entry points or any of these exit points, and how they just all connect. And then then for this being the program model, process model, and resource model for these facilities like files, databases, web services, and message queues, then all the languages are kind of the same. Not all of the languages are the same. There are a few languages that have particularly different ways to approach these things. They're mostly just experimental languages and proof of concept that it could be done any way. You can make any kind of source representation to have any kind of machine representation that you can imagine. These are the ones that are everywhere, and they're just very sensible and sensical, and that's it's one of the nice things is that once you learn a language, then you learn for the program model, process model, and resource model what it's doing, is for writing computer programs, and then it's pretty simple to learn other languages because they all do the same things. So I have like 30 of these for all these different languages over time, because they're each also different, and a computer program is pretty strict in the sense that it's entirely senseless and it can only do exactly what you tell it. This book is great. This is a fellow named Ogden Rood who lived from 1831 to 1902, and so he was a physicist, but he studies color. So he studies optics, light, and color. And this is called The Student's Textbook of Color with Applications to Art and Industry. And its first American edition was 1879 with a preface, introduction, and commentary by Faber Baron. And so what this is about is not just this color and art. Like the other day there was some discussion of art in theory and philosophy, including stuff like, oh, well, any philosophy has to address art. And I like that. But I don't necessarily see it so necessary for the technical. It's just part of an ontology with regards to poesy. It's associated with kind of like this Coleridge language. And then I had mentioned, for example, Suzanne Langer's theory of art, a theory of art that's necessary for this. And then I was reading them from Herbert Reed, and Herbert Reed in the earliest 20th century was a great editor and then when there's talks here before, like about home, T-E home, H-U-L-M-E. And then is regards to that, I found a book the other day by Herbert Reed, and he said that he was expressing the great diversity that arose after modernism. So after Impressionism, after Realism mostly, and then there came to be Surrealism and Modernism and all such forms of what are still considered structured schools of artistic expression, and mostly about painting and graphical design. That Reed said, well, we got Croce, C-R-O-C-E. Croce had arrived at like a theory of art, and then after that, then it goes into Bergson, and so Bergson's kind of like this analytical tradition, and before that, it's kind of like this idealistic tradition, and so that's who Herbert Reed would kind of point to for a theory of art. But here, there's not really a theory of art. But for a theory of color, then we have beyond the models of like rods and cones and perception in the eye, and what it means for like the senses of color, then for optics, and then for actually the behavior of light, and like there's one warm red and then three purples, purple, indigo, and violet, to help affect or reflect this infrared and ultraviolet catastrophes, in a sense, as with regards to how physics makes art optically, or light optically rather, and optically light, and then according to absorption and reflection, and then the transmission and filtering, that there's color, that it's not just luminance, like the lightness or darkness, and then chrominance, meaning red shift or blue shift, which is though how every screen kind of makes luminance, chrominance, and chrominance of the modern way that used to be called RGB, when they had three outputs, red, green, and blue, that today it says with regards to YCBCR, luminance and chrominance, blue shift, and chrominance, red shift. With regards to the CIE, Committee International Déclarage of Color, of the color spaces in regards to these models of color, and usually tri-stimulus color spaces, meaning like XYZ or ABC or red, green, blue, or red, yellow, blue, vis-a-vis the additive and subtractive colors and all these kinds of things that result making inputs that make for matters of perception and perspective with regards to different people's apparatus for the perception of color, rods and cones, and also different kinds of pigments. And then also the different ways that it reaches via the optical chiasma, the optical processing parts of the brain, and then back up to the cognitive and executive functions. Any sort of relation are not two colors. For example, I tend to think in colorblind terms, but I'm happy because sometimes when I dream, and I dream in color, and that some people see more or less, or some people do not have the sense of sight, and these kinds of things. Then though, that color, as is explored by Rood, R-O-O-D, Rood, he makes a pretty great survey and a study of the science of it, and why light and optically is so cool. So one thing I'd mention about that is I've been reading this book by O.W. Richardson. He's an electron theory physicist. He's a theoretical physicist and also an experimental physicist. And so he helps describe the thoughts and learnings that go into the differences between when light is called electromagnetic radiation, like a radio wave is, that it's not necessarily the same thing. They're framed and related into the same system of units in the dimensional analysis of the physics and the science. But electromagnetic radiation, including light, is sort of an overloading of it. It's a dilution of it. This is that the photons and the character of light is massless and chargeless in a world of kinetics and kinetic energy and charge and electromagnetic energy. Have that it just says nothing except it's just some energy in this world of energy and intelligence. This theory of the physics has that optical light is kind of special, and it's the only thing that has this diffraction and refraction going on with respect otherwise to reflection and these models of waves and so on, that thus we have this tri-stimulus color space. That's our theory of light, both as it's reflected and as it's absorbed, and is according to the usual models from art and discussion of the theory of additive and subtractive color with filters and pigments vis-a-vis absorption and reflection and transmission and filtering and absorption and reflection. And that, then this book gets into a little bit more of how about this kind of dual tri-stimulus color space, as its light's always flux and fleeting and gone, and then it's also, as always, as of both sides of the mirror, as it were. So for this part of the aspect of the theory of physics, it helps to reflect that, yes, there is a theory that it's all kind of electromagnetic, but there's also that it's not. And so there's an important apologetics that physics, that's popularization, owes the popular public of the appreciation of science and its theories, and as to why light and its behavior, for example, is with regards to parallax and peripheral parallax, and the way that it's any different than otherwise this electromagnetic radiation is that it is. And so that's a pretty cool thing. So this book then, it was written about Rood's studies of art and paintings. Like here's a painting of Delacroix, and he talks about Van Gogh and Turner, the Valley of Aosta in a snowstorm, Claude Monet, the Impressionists, Renoir. And so he's studying these great painters, Pissarro, the Boulevard Montmartre at night. Though simple in technique, note remarkable effect of luminosity. And so here is that the impressions of the expressions that are made then gets into the books and how the colors and complementary colors and the mixtures of colors and pigments arrive to these different perceptions of these things. And so he talks about principles of harmony on the small interval and on gradation. See, in continuous tone images, there's no boundaries and borders. It's just kind of a constant change through the things that this gets into. But when I picked up this book, and it was from the art and architecture section, that what it had, though, is that it reflects particularly on the special character with regards to light and its behavior of these different things with regards to orange, red, orange, and orange, yellow, with regards to violet, blue, pure violet, and indigo, and these sorts of colors. Because the listing out of the prism of Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, doesn't necessarily reflect exactly what goes on in all these different ways, that there is the gradation of and the reticulation of the color scales, the temperatures sometimes. Although the temperatures is usually as with regards to the intensity of arbitrary light sources, that there are two concepts with regards to light that have that the sun is like arbitrary, the brightest light. And there's measures of that with regards to bright light and white light. And then with regards to black and the blackest black, or pure black sometimes it's called, there's the idea of a body that as a visible body absorbs all light, and then it may emit light. In the theory, this is the idea of the black body radiation, is that the black body radiation is that it absorbs as an ideal body in the theory all the light that reaches it, and then as what it emits, it's different than what reflects light. And so anything in the middle between a black body and an arbitrarily bright object in the sky, or the sun usually, or a candle, is often kind of given a standard candela as the intensity of light, but infinity intensity, or infinity absorption, of these two kinds of complements extremes of color, then has usual kinds of reflections on that being all the colors, or with regards to the polychromatic, the prismatic, and the chromatic, those being two sides of this dual tristimulus color space, as it were, and as with regards to the theory, and as it's arrived at, that this is all quite thoroughly according to the theory of, in our standards and our references that we have to the study of yet what is having for its own particular qualities, the very nature of optical light as reflecting freedom of information as the signal, it's something very particular, and it has a lot going on. So this book is the survey of the late 1800s of the understanding of light with regards to light and its dispersion and aberration and diffraction and reflection, diffraction and reflection and refraction, with regards to color and its perception. And then that Richardson's book that's all about the electron theory of matter very carefully details many places that he, and it's very appreciated, that he conscientiously says, this is where our theory sits these two together. This is where our theory sees these two each their own. So that's how it's relevant then for something like today, when you have something like the Pantone color charts, and when you have colorimeters to be able to figure out what does this really look like to all these different people who see colors variously. Then with regards to the theory overall, then it's possible to arrive at something like, this is how to build a television. This is how to build a color television. This is how to build a camera. And to have it to reflect that it will operate as an optical device, say. So getting into this on the production of color by absorption, and Dr. Pisco's work on the fluorescence of light. There's been some concepts here considering the second spectrum and the third spectrum of light, because optical light is special, and so it kind of has its own way that it has resonance theory. It talks about fluorescence and phosphorescence, kind of like Cherenkov radiation, helping to reflect that electromagnetic light is its own, electromagnetic radiation is its own thing. Then if it's said to include optical light, which is chargeless and massless, it can be left out. They can be two separate things, or three. And then there's nuclear radiation, and the nuclear radiation, because you got, if beta rays are like beta particles and they're electrons, and then gamma rays or like X-rays or Roentgen rays, and they're like optical light, has that light is like the free unstimulated emission of radiation that's like so. And then otherwise, then we get into radionuclear radiation, so that there's at least these three kinds of radiation, but the light is just kind of like more with the radionuclear kind of than the electromagnetic, say. Yet at the same time, it's particular right there in the zone. And it's not so much as like, wow, was light invented so our eyes can see it? It's like, no, our eyes developed over billions and billions of years to see optical light. So, and color, in color. Vis-a-vis imaging. So both imaging and vis-a-vis boundaries and the continuous tone and color are very much so associated with the sense of sight and the perception of films, as Lucretius might have put it 2,000 plus years ago. The green color of vegetation offers a rather peculiar case. So you might have studied plants and how photosynthetically active radiation gives them energy to respire and metabolize their cellulose circulatory networks to live as plants. When we examine with a spectroscope any ordinary green pigment, we find that the red is absent and the blue and violet much weakened, as was the case with emerald green. Green leaves, however, furnish a spectrum of a different character. The extreme red is present and offers a deficiency of colored light, which is followed by an orange-red space. Next comes the orange, then the yellow, greenish yellow, and yellowish green. After this follows a little full green. The The rest of the spectrum decreases rapidly in luminosity. Figure 25 represents the spectrum. So this goes into the ideas that with his spectroscopic analysis, Rood was able to arrive at a lot of these colors we can't see. Yet there are. Invisible color. Some people can see. Some people have more rods and cones, they say, or they have different pigments in their eyes, and they can see. And then he talks about the light at given times of day, like the golden light, or at sunset or sunrise, or like while there is the light to take photographs, to make paintings, or otherwise according to the light of the day, that it varies. And then this is related to the parallax and peripheral parallax. Well, that's about what I thought to talk about, was this programming book for a while, and then this idea of color and the theory of color in the optical light is special, and that it's in its very primary sense, and because it reflects so much information in the very free transit of information, and then if metered according to the light speed and relativity theory, that is its own theoretical milieu and its own super classical first class concept. That's where I'll end today, and this Logos 2000